Okay, we're gonna continue on here, talking about buffers in chapter 14. Was there any questions on anything we talked about leading into the break here? Okay, so hopefully you have a good understanding now of buffers, what they are, how they work, and how to select a buffer in that situation. So let's take a look at some more stuff about buffers, and we'll get into some calculations. This is just a graph again that shows the difference in the pH change between a buffer solution and something like water, which obviously is not a buffer solution. And as we can see, pretty much our buffer solution is going to be able to maintain its pH, even with the addition of a good amount of hydrochloric acid. We definitely will see a pretty big jump in the pH, even with a small amount of hydrochloric acid being added to our non-buffer water solution here. And again, as we talked about, the buffer has a way, again, to basically prevent the formation, in the case of HCl, of free H plus floating around that solution, and thus it's able to keep that pH in check. Water has no way to basically stop the formation of that free H plus, and that's again why we see, as we can see in this graph here, a pretty big jump in the pH, even with a little bit of addition of HCl to it. So take a moment here for each of the following pairs. Can they be a buffer? Okay, so let's take a look and see. Remember, buffer is really one of two combinations, either a weak acid and its salt of its conjugate base or its conjugate base, or it is a weak base and the salt of its conjugate acid. So that's really what we want to determine here. And this is again a situation where perhaps knowing those six or so strong acids would be pretty beneficial. So a reminder there that, that kind of list that we made a few times, I think, along the way here. Strong acids, HCl, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydroiodic acid. So here we have HF and KF. Would that be a buffer? HF and KF, yes, would be a buffer because this is a weak acid. And once again, I don't see it on this list, so that's probably going to be weak. And KF, again, is really a salt that's K plus and F minus. So once again, like my buffer example we just did there a second ago, that is really our two parts of our buffer, which again is only separated by one H plus, basically the Bronsted-Lowry definition in this case. Really, the K plus is a spectator ion kind of just hanging out, not doing much, but that's why it's called the salt of its conjugate base, because it has the K plus there, basically. Now, if we go to B here, which is our HBr and like our KBr is a salt, which is K plus and Br minus. These two guys are related to each other. Would that be a buffer? They would not, because this acid is a strong acid, which we see on our list. So that automatically means it cannot be a buffer, because a buffer itself, again, cannot be composed of a strong acid or strong base, because it won't be able to set up that equilibrium like we talked about. How about C here? That is a little sodium carbonate and a little sodium hydrogen carbonate. That's basically, we get rid of our spectator ions of sodium. That is basically carbonate, and that is basically hydrogen carbonate. The difference between these two is a H plus, yeah. And it's definitely not on our list, so that definitely would be a buffer in this case. It must be a buffer. Any questions on that? By the way, on that particular combination, which one would be the acid? Which one would be the base? Which one would be the acid part of the buffer here? It would be the HCO3, right? Because an acid would be something that needs to donate an H plus, so it's got the H to do that, right? The other guy does not. So the only thing the other guy could do is accept an H plus, right? Which means it would be the base part. So if you have a situation like that, again, the one with the extra H would most likely be the acid part, and the one with one less H would be the base part. Kind of the same idea here, only has an H not to give, right? So it can only accept an H, and obviously this would be our acid. Any questions on any of this? C is, yeah. So in this case, A and C would be buffers. B would not be a buffer in this case. Yeah. Other questions? Okay. All right. Well, we talked about buffer, talked about what they are. So I feel like we should do some calculations. A reminder again that before we get into calculations, or speaking of the calculations, right? I think I said last time, but once again, a buffer really is a common ion situation. And again, that is the place where if you choose so, you could use your Henderson-Hasselbalch equation, or again, you can do a nice table. So when you're doing a calculation, again, it's your preference, whichever way you want to do it. But that is, again, the situation where you could use the Henderson-Hasselbalch equation. So let's try one here and see what happens. Let's start with A. So once you do A, what is the pH of this buffer system that contains 1 molar acetic acid and 1 molar sodium acetate? Here's the Ka value there for acetic acid on the bottom. So take a moment there, calculate up the pH of part A. Let's take a look at A here. So we have a 1 molar acetic acid with 1 molar sodium acetate. And we have a Ka value for acetic acid of 1.8 times 10 to the minus 5. All right, so they were nice enough to tell you it's a buffer, but once again, they're not always going to tell you it's a buffer. So once again, you do need to be able to recognize first off that these two things are related to each other. And once again, if you get rid of that sodium there, that's pretty much our conjugate base and our weak acid there. So that is a buffer situation that's happening. And that is what you, again, will, in a lot of cases, has to just recognize yourself because they're not going to flash it with big lights that, hey, this is a buffer happening here. So again, that is your buffer. So because you can recognize it hopefully as a buffer or know that it's a buffer, you again do have two options as to how you would want to solve it. Probably the easiest option would be to go into your Henderson-Hasselbalch equation, which is our pKa plus the log of your base over your acid, where our pKa is equal to minus the log of the Ka value. And if we do that, we would calculate our pKa, which would be minus the log of 1.8 times 10 to the minus 5. There's that magical 4.74 number that always seems to pop up when we talk about buffers. That will go into our equation here. pH is equal to, put the number in, 4.74 plus the log. In this case, the base is 1 molar. The acid is 1 molar. As we talked about a second ago, that's pretty much going to give you a 0 because that's the log of 1, which means our opening pH here for our buffer will be a 4.74 for this particular one. Question on that there. Now, again, if you chose to do the ice table, perfectly fine. You would want to most likely set up the equilibrium with our weak acid, which is our acetic acid, breaking apart into H plus and our acetate. Remember, again, if you choose the ice table approach for these buffer type problems, you should have 1 molar there, 0. And again, really important to have the 1 molar there, or you're not really doing a buffer problem. Again, the rest of the table here would be like kind of normal. Our 1 minus x, our 1 plus x. Once again, this would go into our Ka. You would solve for x. And that would equal your H plus concentration, which then you could go into your pH and should end up obviously with the same answer as we got there. You could make an assumption if you needed to, like normal, and you'll end up with hopefully the same answer. Any questions? Okay. Just wondering. Everybody's like looking that way. All right. Any questions on A here? All right. So now that we have a buffer, we're going to take this buffer and we're going to add some acid to it, which is part B. So let's talk about how we go about doing this. So in part B here, we're going to take the exact same buffer we had in part A, and which means we're going to have our acetic acid basically here, setting up our equilibrium that has our acid and base in there. And now we're going to add some HCl to this, which once again is a source of H plus and Cl minus. So as we talked about in terms of how a buffer works, we are going to get a reaction here, right? So we're going to get a reaction since we're adding HCl, as we talked about last time, it is going to react with the base part of the buffer, which in this case is the sodium acetate. So we're going to get an actual reaction is going to take place, which is going to require us to do an ice table here to figure out, what happened to our buffer so that we can actually figure out what the pH is at the end of the ice table. In this particular problem, we're just going to assume that everybody's volume just stays at 1 liter. Just for this particular problem, that's not normally the situation. Normally, you do have to take the sort of liters into account and the volumes into account. So just kind of keep the numbers not too bad here. We're just going to, everybody's just 1 liter. So when I add volume, which is a very important idea here, right? When I add volume to another volume, does the molarity stay the same? So if you took a volume of one thing and mixed it together, say like in a test tube, say in a beaker here, does the molarity stay the same? Or does it change? It does change, right? Which is why all those experiments we did, you had to do like the M1 V1 equals M2 V2 sort of calculation, right? So molarity doesn't change because if you think about really what molarity is, it is moles of solute over liters of solution. And that means that the solution part will continuously change as you're adding volume, and the molarity will continuously change. The one thing that actually doesn't change is the moles of the solute. And that's actually what's reacting here. It's actually the solute that's in the solution, those guys floating around, the acetates, acetic acid. Those are the guys actually reacting with each other. And the moles of those guys don't change. They are what they are in that case. So one really important thing when we go to do an ice table in any situation, which is one of the situations here, you have a buffer and you add some volume to it, some acid or base to it, you need to do the ice table initially in moles because they do not change. Molarity does change. Same thing's going to happen when we talk about titrations, right? Because in titrations, we're doing nothing but continuously adding volume, right? Which means the molarity is continuously changing, but the moles will remain the same. So those are two very common places that when you have to do an ice table, and again, these are the small things that we were talking about that you got to keep aware of as you're doing these things, that you have to do it in moles. What you should do after the first ice table and you do it in moles is to be in a safe spot in most cases, convert it back to molarity at the end of the ice table. And you would do that by the total volume that you added together. So we want to do the ice table in moles and then immediately convert whatever we get in the equilibrium line back into molarity, because in most cases, that's going to put it in the correct unit that you need to continue on with whatever else you may be continuing on. So let's see how this works. So we know, as we talked about, that the HCl in this case is going to react with our sodium acetate. So in part B, we have our same buffer. We have our 1 molar acetic acid. We have our 1 molar sodium acetate. And we still have the same Ka value. But in this case, we're going to add, was it 0.1 molar, I believe, right? 0.1 molar HCl, if I'm not mistaken, I think that's what it said. 0.1 molar HCl, yep. Okay, so we're going to start with an ice table, which means we're going to start with our reaction, which is going to be our hydrochloric acid. Once it goes for a swim, we'll then find the base part of the buffer, which in this case is our sodium acetate. And those two are going to react and basically do a double displacement reaction, right? So we got a positive, negative. So we're going to swap partners here. And that's going to give us a sodium acetate. No, it's not. It's going to give us a sodium chloride, which is sort of like sodium acetate if you wrote the wrong thing. Let's try it again. Actually, I think I was writing the right thing. We got a sodium chloride happening there. And we have an acetic acid. That's what I was trying to say in this case. All right. So as I mentioned before, we're going to do this ice table here in moles. And in this particular case, we're just going to assume everybody is 1 liter. So everybody's going to have a volume of 1 liter. That makes the math pretty easy, right? Because my moles here initially for HCl would be 1 liter times 0.1 moles per liter is 0.1 moles for my HCl. And again, these are moles. My sodium acetate would be 1 liter times 1, which is 1 mole. Nothing here for my sodium chloride. And my acetic acid would be 1 liter times 1 molar, which would give me 1 mole. Once again, if I do not put this guy on this side, it is not a buffer, right? So super common mistake. Yeah. So again, you got to have something on both sides for it to be a buffer. Any questions on that now? So when I toss my HCl into this buffer, right? What's going to happen is we're going to get this reaction that's going to occur. And what I want to know is what should happen to the HCl? Should it still remain? Should it kind of get used up? What's going to happen in this case? If this is a good buffer, should I have any HCl when I'm done? No, right? And that means in this case, slightly different is I already know what the change is. It's not X. I know this is a buffer, which means it should use up all of the HCl that I just added, which means the change here is actually going to be the amount of moles of HCl, which, by the way, in comparison between this guy here and this one here, which one is the larger number? Sodium acetate, which means in this case, the sodium acetate is the excess reagent. The HCl, which is the smaller number, is the limiting reagent. And logic, which you should always think about when you're doing problems, is if I took the bigger number, what would I end up with? What type of number? If I subtracted the bigger number from the smaller number, I would end up with a negative number, which you can't have, right? So always, even though you're not going to want to do it in certain situations, you will have this conversation with yourself as you're working out problems. Bless you. You'll think to yourself, I shouldn't use this number. Always take the small number. Yeah. Don't be the person that puts the negative number in there and the larger number. Even though your mind's going to tell you, I don't think it's the right number. Always take the small number and you'll be fine. All right, those are words of wisdom. Not sure much how wisdom there was, but there's some. And that's going to be minus here. This is going to be plus 0.1 moles on this side. By the way, why am I completely ignoring sodium chloride? It's what type of salt? The neutral salt, which means it's not going to have any effect on the pH. So why put numbers there that I'm not going to use correctly and shouldn't be using anyways? So might as well just leave it out in this situation. That means that when we get to equilibrium here, I'm going to grab my calculator because it's been a long week. So I'm going to go with 0 on that first one there. I'm going to go with 1 minus 0.1. I think that is 0.9 moles. I'm going to also add that one and not subtract it like I have a tendency to try to do. And I'm going to end up with 1.1 moles. First off, any questions on the ice table? So again, like an ice table, but again, slightly different than what we've done before. We already know what the change is. We have to do it in moles because we're adding volume. And I would say typically when you're doing an ice table in moles, you probably will know the change. So you'll have like an actual number in a lot of cases for the change part, not like X's. I would say 9 times out of 10, you'll be rolling X's with molarities if you're throwing that in there. But when you're adding volumes, you got moles, a lot of times you will have a number as the change part and stuff like that. Not always, but most of the time, that's the situation. Any questions on that? When I figured out what the change was, the truthful answer is it's a buffer, right? Which means we know that the definition of a buffer is any additional acid or base that you add in there should kind of get used up in a sense and should be tied up in whatever it's reacting with, basically, right? And that's what prevents the formation of free H plus or OH minus. Just logically thinking about it, when you look at the numbers in your ice table, which sometimes people just kind of put the numbers in the ice table and don't really actually look at, what the ice table is telling you. The number difference between the two is the HCl is much less moles than the other one, which means the HCl in this case is going to be the limiting reagent and the sodium acetate is going to be the excess reagent. So it's always the limiting reagents can get used up first. So that's why I said the small number thing. It's always going to be the small number. Yeah. Even though there will be certain situations, and it may not make any sense what I'm saying right now, where your mind's going to tell you it's not the small number, but it's going to always be the smallest number. And there will be some calculations later on where people always go like, no, it can't be. I'm just going to use the negative, even though I know I shouldn't be using the negative and get a negative number. They always use the wrong number. Other questions on that? So at this point, once you've done this first table, I would throw it into automatic gear at this point and convert everybody back into molarity. And I would do that because 9 times out of 10, that is going to be the unit that you need everybody in. Technically speaking, you don't necessarily have to do it at this point, but it's a very good practice for other calculations we're going to do down the road. So to do our molarity in this case, we would divide by our total volume, which in this case, we are keeping at 1 liter, which is not always the case. So you would have to figure out in this case, if we weren't keeping constant volume, how much volume of buffer we had and how much volume of acid we added in, and that would get you your total volume. It does need to be in liters, obviously, so you want to make sure it's in liters in this case. So in this case, this is going to give me 0.9 molar here and 1.1 molar here. So as I was just mentioning, a lot of times people don't really look at their ice table in terms of understanding that it can really help you sort of figure out what is going on. So you do this ice table because frankly, you don't know what's going on and you know that maybe you should do an ice table. And now you get to the end and go, I still need to figure out how to get to the pH, right? So you could look at your ice table and see pretty much what you have left over at this point, which is this guy and this guy. So pretty much what I have left over at this point, if I did not already know what this is a weak acid and its conjugate base, which is also known as a buffer. So again, if the problem didn't tell you it was a buffer, you should look at your ice table and see what you got left over at that point that has numbers pretty much. And it will oftentimes tell you kind of what you should do next if you're not sure. So if you could recognize that at this point as a buffer, we now know to figure out our pH. All we have to do is use our Henderson-Hasselbalch, or again, you could use another ice table, but I'm going to use the Henderson-Hasselbalch here. The pKa value is still based off of acetic acid, which is the same one we used in the previous part. So that's going to be 4.74 plus the log. And again, we want to make sure we get our base, which is this guy here, 1 less hydrogen over our acid. And now we can do this here, 0.9 divided by 1.1, a little log action, and a 4.74. That's going to give us a 4.65, yeah, as our pH. Yeah. First off, any questions on that? Yeah.
Quick clarification.
Yeah.
So you always want us to use molarity for the base and acid for this formula?
Yeah, so the truthful answer is you can leave it in moles. In this one specific situation, if you go into the Henderson-Hasselbalch equation. If you go into an ice table, you should have it probably in molarity. So that's the only place where you could leave it in moles. You get the same answer because when you use this equation, the volume on top and bottom where you're dividing there will cancel out. So it'll work out the same. But there's a lot of places where we're going to do a table like this where you 100% need it in molarity to continue on with the next type of calculation. And if you don't have it, you're going to get the wrong answer. So my opinion would be throw it into molarity when you do this. And even if you're not going to go into the Henderson-Hasselbalch equation, you will have those numbers in the correct units that you need for the next calculation for sure. Yeah.
If one was to be a nice table after this, it would just look a lot like the ice table we did.
Yeah, so I was just gonna write that. So if your question is if you chose not to do the Henderson-Hasselbalch but want to do the ice table, the probably easiest way to do it would be just like part A, which means you would use the acetic acid as your equation dissociating. And in this case, what you would use is actually your equilibrium concentrations as your initial. And again, this would be really important to make sure you get everybody on the right side and that they're in molarity as well. And this would be 0. And again, we would need this guy over here. And then at this point, you would go back to your x's. Yep. And you would solve, obviously, for the x in that case, using your Ka value. And again, you should get the exact same thing that you got with your Henderson-Hasselbalch equation. Yeah. Other questions on that? By the way, did our buffer kind of do the right thing? Let's see. We initially started with a buffer that had a pH of 4.74. We added some acid. It went down to only 4.65, not a giant drop, but it did move in the correct direction, right? Because we added acid, it went down. So if you did this calculation and your pH went up, you screwed up somewhere, yeah, because it's not going in the right direction. So these are things that you want to really kind of think about as you kind of do these buffers and stuff like that. Question on that there. All right. So while we have this example up here, I'm going to use it to demonstrate what I was talking about a second ago when we were talking about buffer capacity. So I'm going to try to carefully erase most things here. Without erasing too much of what I might need here. And then maybe we'll just get rid of these guys down here. And we'll get rid of this guy right here, right? Okay, let's say we have this same buffer, for example, and it worked really well in this example, right? When we added our 0.1 molar HCl, and that was in range with the molarity of our buffer, which was about 1 molar. So let's just say you're doing this and you're talking to your friend and you go back there to the back cabinet where they keep all the acids, and maybe you don't grab the 0.1 molar, but maybe you grabbed the 18 molar hydrochloric acid. Hopefully you stayed in the fume hood with that and didn't bring it back to your bench. But let's just say you grabbed the wrong bottle and you threw in there a liter of it. some chance, right? So you threw 1 liter of it, that gives me 18 moles of my HCl, right? So if I throw my 18 moles of my HCl in here, now who's the limiting reagent? Yeah, the acetate is no chance and no chance at all to take care of all that. So what's going to happen in this case is now your acid that you added is actually the excess reagent. This will actually be your limiting reagent. And what will happen, the change here will actually be 1 mole all the way across because you grabbed perhaps the wrong thing. And what you will actually end up with here is about 17 moles of your HCl still left. You'll actually end up with none of these guys, right? And you will end up with like 1.1 moles of this. Do I still have a buffer at this point? I don't, and I can see that from my ice table. I have acetic acid, which is a weak acid, and I also have HCl left over, which is a strong acid, right? My pH is going to go crazily down pretty far, negative off the scale probably, and stuff like that. So this is what I was talking about earlier in terms of buffer capacity. Really, the things reacting when you have a buffer or when you add things to your buffer is that solute. In this case, the acetic acid, the sodium acetate, and you only have so many moles of those guys floating around in there to handle any incoming acid or base. So again, if you don't think about the molarity and the moles of the acid or base you're adding, and you just make a buffer that's not of the correct molarity, it may not be very effective buffer at all. Or if you add too strong of an acid or base, even though technically you made a buffer, it may not be strong enough in a sense to handle what's coming in, and you could blow right through it. And obviously in this point, you would just have a ton of H plus all over the place, right? From that HCl that's coming in. And again, that's going to be a giant drop in the pH. Any questions on that there? All right. So nobody do that, by the way. Yes. I grabbed the liter of HCl, 18 molar. Is that okay? All right, let's try this one here to start out with. We got this buffer here, and we're not keeping the volume constant. So we want to know what is the pH of the buffer before we do anything to it, and what will be the pH of the buffer after we add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer. I'll give you a Ka value for NH4 plus. It is 5.6 times 10 to the minus 10. I'll go off the top of my head and hope for the best. All right, so we're looking for two answers here. What is the pH of the buffer before you do anything to it? And then what is the pH after you add that sodium hydroxide to it? Okay, let's take a look, see how you're doing. So first off, they weren't nice enough to tell you it's a buffer. You should hopefully be able to recognize this as NH3. And our NH4Cl is really a salt that's NH4 plus and Cl minus, which means really our buffer components here are these two things, right? And they are related to each other by 1H plus, right? By the way, the acid part here would be which one? Yeah, that would be the acid. This would be the base. Now, by the way, you may not be able to find that Ka value that I gave you in a table, but you might be able to find the Kb value for NH3, which is something like 1.8 times 10 to the minus 5, right? And if I wanted the Ka value, that is where we could use something else we saw earlier, Kw equals Ka times Kb, right? To convert it into our Ka value. By the way, the other thing we could have done is, since we know we need a pKa value, we could have took the pKb, right, minus the log of the Kb, and that would get you like a 4.74. And then you could take the pKa is equal to 14 minus 4.74 as well. So you could go with that approach as well. So again, there's many different ways you could kind of do it. And if you can't find like NH4 plus in there, then maybe you need to look at the Kb table to find, that value. And again, you could convert it to the Ka and then just get the pKa value as well. Any questions on any of those relationships there? All right, so now we have all those relationships. So let me get rid of it so I have somewhere to write, I think. So let's see this here. All right, so since I did give you the Ka value, I'm just going to use that Ka value, and I know it's a buffer. So probably, again, the easiest thing to do to get the pH of our buffer here to begin with, it's just to go into our Henderson-Hasselbalch equation. And that means we do need the pKa value of minus the log of 5.6 times 10 to the minus 10. And that should get us something like a 9.25. By the way, as well, this is a basic one, so you could use that POH version of the Henderson-Hasselbalch if you chose to go that route as well with the Kb value. But you really need the pH, so why do that? So the pH here is going to be 9.25 plus the log of our base, which would be our NH3 in this case. And that is going to be 0.3, it looks like, divided by our 0.36, which is our acid. And that's going to give us an opening pH here for this buffer of, I'll call it 9.17 in this case, yeah. I could go into the Henderson-Hasselbalch equation here with molarity. I could do an ice table with molarity because we haven't added any volume to anybody, right? So it's just a solution. We haven't added any additional volume. Any questions on that? Again, here in terms of the ice table, if you chose to do that route, you could do it as NH4 plus goes to H plus and NH3 using the Ka value. Could also do it as like a Kb problem, NH3 going to NH4 plus using the Kb. But again, that will get you to the POH and then you gotta get to the pH. So again, there's a few different ways you can kind of get yourself, to the end answer here. The simplest and probably most straightforward way would be Henderson-Hasselbalch again along the way. Any questions on that there? All right, so now we're going to actually add some sodium hydroxide here to this buffer. Yeah. It is the acid. Did I put it backwards? No, because we're using the Henderson-Hasselbalch, so it should be base on top divided by acid. It is the opposite way if you use the POH version of it, and you would be using the PKB. So it should always be base over acid with the Henderson-Hasselbalch. Other questions? Yeah. So we're going to add some sodium hydroxide here to this buffer. So clearly sodium hydroxide is a base, right? So when it reacts with this buffer, it should go find the acid part of the buffer in this case, right? Now it's your call. If you want to keep the chloride on there, you can, or you can leave it off. I'll keep it on if you like. So we'll do a little NaOH plus a little ammonium chloride. And in this case, you can get a few different things. You're going to get a little sodium chloride coming out. You are always going to make the other part of the buffer, which means you are going to get some ammonia coming out. And dare I say, you will get a little bit of water as well, a trifecta there on the back end here, in terms of those three things. Yeah. So again, if you leave the chloride out, you can if you want, but you actually get these three things. Now, this ice table that we're going to do, and by the way, that's a double displacement reaction happening coming this way, where really the NH4 is going to be donating its H plus over to the OH part, and that's where we're going to get the water from. We need to do it in moles or molarity? Moles, right? Because we're now adding volume, right, to our buffer, so we need to do that. Here, we're not keeping everybody constant, so we do have some volumes of everybody. So we do need to do that calculation. So we'll go back up here to do it, I think. Get rid of some of this here. So we got some room. All right, so we're going to take the moles of the sodium hydroxide, which we're going to add 20 milliliters of it. Remember, we do want moles, so we want to convert that to liters. So that's going to be 0.020 liters if you divide it by 1,000. We're going to multiply that by the molarity of our sodium hydroxide, which is 0.05 moles per liter. Liters will cancel, and that's going to get us 0.02 times 0.05, a little 0.001 moles here for our sodium hydroxide. So I'll pop that into our table here. We're going to do the same sort of calculation for our buffer. We have 80 milliliters of our buffer. That 80 milliliters goes for both parts of the buffer or just one part? It goes for both parts, right? Because the buffer has both of those things in the beaker together, right? So that is the volume for both of them. So for our NH3, it would be 0.08 liters, which is our 80 milliliters converted to liters. We're going to times it by our molarity there for our NH3, which is 0.3 moles per liter. And that's going to give us 0.08 times 0.3, 0.024 moles of our, this was NH3. That was sodium hydroxide. We'll do the same calculation because, again, it's the same volume because they're in the same beaker. for our NH4 plus, which is 0.36 moles per liter. Gets us 0.0288 moles of NH4 plus. Any questions on that calculation? So we're going to put those into our table as well. And I think I can get rid of my arrows here so I don't got too much going on there. There we go. All right, so into our table will go our NH4 plus, which is 0.0288. And over here for NH3, 0.024. Once again, should I even worry about sodium chloride or the water? No, because neither one's doing anything, right? So again, don't worry about them or put numbers or anything like that. Once again, this is a buffer. So at this point, when I dump my sodium hydroxide in there, all my sodium hydroxide should get used up. It is the limiting reagent. Once again, if you just logically look at it, it is the smaller number, right? So again, always the smaller number. So we're going to take our smaller number here, which is our sodium hydroxide, which is really the limiting reagent here. And we're going to go minus 0.001, minus 0.001, and now a plus 0.001. At equilibrium here, we got 0, this guy, and 0.0288 minus 0.001. 0.0278 moles. And remember, on the right-hand side here, we're actually adding, not subtracting. So make sure you do that. 0.025 moles. At this point, I should convert these guys now back into molarity. Here, we do need to figure out our total volume, right? We had 80 milliliters for our buffer, and to that 80 milliliters, we added 20 milliliters of base, which means at this point in the process here, we have a total volume of 100 milliliters, which we do need to convert to liters. So we're going to divide it by 1,000, which means we're going to divide this by 0.1 liter here to convert us into molarity. And that will get us here 0.0278 divided by 0.1, a little 0.278 molar, and 0.025 divided by 0.1, 0.25 molar. Any questions on that ice table there? Once again, you should always look at your ice table if you're not sure what's happening at this point. And what we can see from our ice table is what I have left over is NH3 and NH4Cl. Once again, these two things are related to each other. That is, again, a weak base in this conjugate acid, which is also, again, still a buffer. So your ice table does give you a lot of information about what you have, what's left over, and sometimes people just sort of gloss over the ice table. And this, again, is why it's really important to be able to write these equations correctly so that you are looking at the correct thing at the end of your ice table. That means, once again, we could go into our Henderson-Hasselbalch equation. That will give us our pH is equal to our pKa plus the log of the base over the acid. It's going to be the same pKa value we used previously, which is our 9.25, plus the log. Once again, we want to make sure we get our base up on top, which is 0.25, and our acid on the bottom, 278. And that's going to get us a pH here of 9.20. Yeah. Did this buffer work good? It did. It only went up like 0.03, right? And it also went in the correct direction, right? Since we added base, it went up, right? And again, if it went the other way, that's not so good. Yeah. Any questions on that one there? Yeah.
You chose 0.80 for ammonia
Why did I choose points?
for the leaves on
Because that's what the problem said. We added the 20 milliliters to 80 milliliters of the buffer. So remember that the buffer, right, would consist of both of those things in this case, right? They're both floating around the same beaker, and it has a total volume of 80 milliliters. Yeah. So that 80 milliliters goes for both parts of the buffer because they're basically in the same beaker. Yeah. Other questions? Yeah.
So, pH high, it's, and that's it. Yeah. Well, that's good enough.
It's actually high because this is really a buffer made up of a weak base and its conjugate acid. So although we are using the conjugate acid as the Ka value, this is really a weak base, and that's why its starting pH, as you see there, is 9.17, and that's because really the kind of pKa of like ammonia would be 9.25, which is basic. So this is what I was saying about. This would be a really good choice if you wanted to make a buffer in that 9-ish range. This would be the one that you would want to choose. And you would really get the NH4 plus in a lot of cases from the ammonia, right? It's a weak base. So ammonia is in when ammonia, for example, is in water, right? And you go to get it, like when you did your group 1 experiment, right? It didn't say ammonia, but it was ammonium hydroxide, right? And that's basically because when ammonia is in water, it makes NH4 plus, and that's the equilibrium that's actually being set up. That's why it's basic. Other questions? All right, one more here, just to make sure. We're going to use the same deal here, except we're not going to add 20 milliliters of sodium hydroxide. I'm just going to make it up and hope for the best, so I'll do it with you. We're going to use this exact same 80 milliliters of this same buffer, and we're going to add, why not? Let's go with, I don't know. Let's go with 25 milliliters of 0.3 why not? I'll try it. Molar hydrochloric acid. What would be the pH of that? I'm gonna quickly make sure I picked a good number before you get too far into it, hopefully. So again, to that 80 milliliters of that buffer there, we're going to add this guy there. I think we'll be okay. We'll go for it. 25 milliliters of 0.3 molar HCl to this buffer. What would be the pH? So let's take a look. So we're going to take our same 80 milliliter buffer, and now instead of adding the sodium hydroxide to it here, we're going to add some HCl to it. So we clearly know we're going to get a reaction. We need to do an ice table, and obviously we need some moles. So I'm going to get some moles of the HCl we're adding. Again, we're going to convert our 25 milliliters into liters by dividing by 1,000. We're going to multiply it by the molarity of our HCl, which I made up of 0.3 moles per liter. I guess we'll see how I did here in a bit. That's going to get us, looks like 0.0075 moles of HCl. Now, when I do add the HCl to this buffer, it's going to react with which thing? The NH3 or the NH4Cl? It is going to react with the NH4 because that is the acid part of the buffer, right? And that is the base part of the buffer. And since this is an acid, it will go and find the NH3. Did I say that right? I said that backwards. I think somebody said that right, and I may have said it backwards. So it will react with the NH3 in this case, which is our base part of the buffer. So I do think I said it backwards. So it will react with this guy here. And that will give us our acid-base reaction that's going to happen. Obviously, our moles of our NH3 and NH4 plus will be the same. So I'm going to flip a page here, and we're going to roll the equations. So once again, adding that HCl, we'll find the base part of the buffer, and that is the NH3 in this case. And really, what's going to happen is he's going to send over an H plus, and that is going to get you your NH4 plus and a little Cl minus. Now, if you want to keep them together, you can, or you can keep them separated like this. If it helps you kind of see the parts of the buffer by keeping them separated, you might want to do that. But you can leave them together as NH4Cl if you want. We're going to again do this ice table in moles. So we just calculated their 0.0075 moles of our HCl. Once again, our buffer is going to stay the same here. So I got 0.024 moles of this guy here. And for our NH3, our NH4 plus, we have 0.0288 moles. And since I kept my CL sort of separate, I'm not going to worry about it because, again, it is a neutral salt, right? So it's not really going to do anything. So I'm just going to kind of not pretty much put any numbers there. Now, in this case, the change here should be the HCl that we added, which would be minus 0.0075, as this is really the limiting reagent in this case. And that's going to be minus 0.0075. And then that will be a plus 0.0075. And these are all moles here. That's going to give us none of our HCl, which is what we expect because it is a buffer. We're going to go 0.024 minus 0.0075, 0.0165 moles of our NH3. And again, we're going to be adding on the back end here, not subtracting. So we're adding over here on the right-hand side, 0.0363 moles. Any questions on the ice table here? Again, just to sort of do good practice here, we're going to turn these guys back into molarity, even though technically speaking, you might not need to, but it'd be a good idea to do it anyways. Our total volume in this case would be, we had 80 milliliters of the buffer, and I did 25 milliliters, right, of our acid in this case. So that's going to give us 82. No, that's not right. 105 seems much better. There you go. And that means that we're going to convert that into liters, divide it by 1,000 or move the decimal place, which will give us 0.105 liters in each of these cases. And now we got 0.0165 divided by 0.105, 0.157 molar, and 0.0363 divided by 0.105. 0.346 molar. Once again, the benefit of the ice table is if you're still not really sure what you're left with, all you have to do is pretty much circle what has numbers. And again, hopefully that should visualize to you that these guys are still related to each other. And this is still a buffer at this point, as we have our weak base and conjugate acid. So again, you can ice table it up if you want to for a second time around, or the easier move back into our Henderson-Hasselbalch equation, which once again is the only place we should be using this is in a buffer situation. pKa value is still going to be the same pKa value we had previously, which is our 9.25, plus the log of our base, which is 0.157 divided by 0.346. That's going to be a 0.157 divided by 0.346, a little log action, and a 925. That's going to go an 8.91 by adding our acid. Any questions on that? So in this buffer, we started out with a buffer just by itself at a pH of 9.17. We added some sodium hydroxide or base to the buffer. We saw the pH go up to 9.2, not a big jump, but moved in the correct direction, going upwards. We then took our same 9.17 buffer and added some strong acid to it, dropped down to 8.9, a little bit more of a jump, but still not a tremendously giant jump in pH, but also moved in the correct direction, right? It went down because we added acid. So again, if you did this calculation, you went above 9.17 by adding acid, something definitely wrong with your calculation. You're going in the wrong direction. So these are the things that you want to watch out for definitely in this chapter and the next one as we go through. as you can hopefully see, it's a lot of the similar type of calculation, but there's a lot of little things that you do have to sort of understand what's going on in the problem so that you don't miss them because they will screw up your calculations. So again, as I mentioned earlier, this is where the conceptual of understanding what's happening and how to do the math is really, really important. And sometimes in these two chapters, understanding what is really going on in the problem is more important sometimes than the math part of it so that you can do the math correctly. So any questions on any of that and what turned out to be our big day of buffers? Yes,